Animation allows us to create whatever we can imagine, such as this simple motor shaft motion. This piqued my interest to find a general solution to bridge between animation and reality. For our power input, we're using a female DC jack barrel. This will be connected to a laptop charger. To control the motor, we're using Adafruit's motor controller hat. This generates the PWM signals needed to control the motor. For our computer, we're using a Raspberry Pi 4 Model B, which is running Ubuntu as well as ROS 2. And we'll also be using a buck converter to drop down the voltage of our laptop charger for our motor controller. I've chosen to use Pololu's micro DC motor, as you can purchase these along with Pololu's magnetic incremental encoder, and these sensors will allow us to measure the speed as well as direction of the motor. We'll be using the software Blender for our animation. First we model a very simple motor shaft. We can then move the shaft to various positions and insert a keyframe. Blender can then animate between these keyframes. Blender also supports Python scripting. This will allow us to log the rotational velocity values of the motor shaft at each keyframe. This information will be fed into the control system. Above you can see a diagram of the initial speed controller design. As I mentioned before, the motor is controlled by a PWM signal. An equation relating the motor speed and the signal can be calculated experimentally, and this is shown as GP open bracket S close bracket. So if we have a desired output shaft speed, we can use this equation to determine the PWM signal required. However, this is a static process, and it doesn't account for any errors in our equation or disturbances from the external environment, such as my fingers pressing down and adding resistance to the motor. So, as you can see on the right hand side, the motor speed visibly changes from its set point of 1200 counts per second. To create a robust speed controller, we need to utilize our incremental encoder to create a PI negative feedback controller. Our new controller implements feedback using the motor speed measurements from the incremental encoder. We can now inject the error between the desired speed and true speed into the PI controller. This system is much more effective at maintaining a zero error between the desired and real motor speeds than the previous system. As you can see, the motor speed remains very near to the set point of 1200 counts per second, regardless of whether I add resistance to the motor by pressing down on it. Now that we have a well-performing motor speed controller, we can follow the motion of our Blender animation.